And you'll see that the identity function is indeed something of type transform, i.e. something of type false to false. The identity function is a false to false function. And then translate P on the second from the bottom green line on the slide. What semantics is that going to have? Well, it'll be a transform which is a false to false function, and P plus is a false to false function. It's the thing that takes Q and gives you P plus Q. And finally, compose, if this is the semantics of one transformation and this is the semantics of another transformation, this is a B2B function, this is a T is a B2B function, U is a B2B function, we have to make a B2B function out of them, well, we just compose them together. T compose U. So I can make a deeply embedded domain-specific language and then give it semantics, or I could straight away give it semantics. I can make it do that with a shallow embedding. So that's the technique we were discussing yesterday, and it manifests itself here in this diagrams language by an alternative way of doing transformations. Now, here's a big watch of code. So remember my pictures themselves were recursively structured things. This picture is itself made out of pictures above pictures and pictures beside pictures and so on. So it's a tree-shaped thing. It's a recursively structured thing. When it comes to turning this, to drawing this, to turning this into an SVG file, then what I want is somehow a list of instructions to a drawing package. To say, put this rectangle here, and put this circle there, and put this triangle somewhere else. I want a list of instructions, not a tree. So I generally can't give a tree to a drawing package. I just have to say, put these things in these various places. So I need to do some kind of translation of languages from this tree-structured language of pictures to a simpler language that I can give to my drawing package. And the simpler language here is I'm going to turn a tree structure picture into a list of basic transformed styled shapes. So this is the list of instructions. It'll say draw this ellipse here, and this triangle here, and this rectangle here, and so on. And then you'll end up with the picture that you had in mind. So you can think of this as being a compilation, in the sense of programming language compilation. This is my source language, and I'm going to compile it into a list of instructions, my machine code. Except my machine code is for a drawing machine, it's not for a calculation machine. So again, you might think, who writes compilers? Very few people write compilers. We have a Java compiler, we have a C compiler, we have a Haskell compiler. That's 3 people. Well, and there's actually lots of people involved in any one of those compilers, but there's 3 teams. And most programmers are not going to be writing compilers. Well, I think that's wrong. And I think it's wrong for the same reason that thinking none of us is language designers is wrong. We're all language designers, and we all do translations from one language to another language. You read in some XML and convert it into something else. That's a compilation process. It's a language translation is a compilation process. And that's what we do. And this is an example of it here, a simple example that I can talk about in an hour or so. But it's an example, and these techniques are useful for lots of what we do in programming. So anyway, my object code is a list. That's the square brackets up here. It's a list of triples. So there's the round brackets with 2 commas. That's 3 things in each triple: a transform, a style sheet, and a shape. And so this stick figure of a girl here, that's going to translate into a list of 1, 2, 3, 4, 5, 6, 7, 8, 9 instructions. And one instruction will say, take the shape, the circle, the ellipse of width 3 and height 3. So the third thing in the triple for the first instruction will be the ellipse shape. The second thing will be the style sheet that says fill it in pink. And the first thing will be the translation, which will be shift it up a little bit so it's here. And then for the arms, that instruction will be, here's the shape, it's a rectangle that's 10 wide and 1 high. Here's the style sheet, it's fill it in red and make the stroke width 0. And here's the transform, again, shift it up a bit, so that it goes here. But they're not all shift up, shift down. So the leg will be a blue rectangle shifted down a bit and left a bit, or down a bit and right a bit. So the various transformations put these various shapes in the right place. And I'm also going to maintain the invariant for simplicity in the definition. I'm going to maintain the invariant that one of these drawings is centered on the origin. So I have some flexibility here in making my stick figure. I could put the origin sort of here in the middle of the circle, and then I'd have to shift the circle. I wouldn't have to shift the circle at all. And the arms would go down, and the body would go down a bit further, and the legs would go down further still. Or I could put the origin here in the middle of the body, then maybe the triangle doesn't need to shift at all, and then some things will need to shift up, and some things will need to shift down. Or I could put the origin over here, and then everything would need to shift to the right a bit. I can put the origin wherever I like. So I'm going to say, I'm going to put the origin in the middle. That seems like a sensible thing to do. So the origin will be in the middle, and some of the figures will be up, and some of the figures will be down. Some of the shapes will be up, some will be down, some will be right, some will be left. But overall, the center of this picture will be at the origin. And here's my program for doing it. I think it's on. So this is right. So these are some functions on these things here. So let's say an extent. So this is kind of the bounding box around part of a drawing, and the extent is a pair of coordinates. It's the lower left corner and the upper right corner. So two positions. That will be the extent. So let me have another picture. I've rubbed out the previous picture. Well, I didn't. I'll have to do it. No, I rubbed it out. So here's one picture, one drawing, and this is its lower left corner, and this is its upper right corner, and that's the extent, that pair of points. And then if I have another one, which maybe is a rectangle beside another rectangle, the extent of that, the bounding box is the smallest rectangle that fits around the thing you're talking about. So that has an extent whose lower left corner here and whose upper right corner is there. So now there's a function here called union that takes those two extents and makes the extent of the whole thing. So that's the smallest rectangle that fits around those together. And what you need to do is compute this point and compute this point, the lower left corner and the upper right corner. So how am I going to do that? Well, if the first rectangle is lower left x1, lower left y1, and upper right x1, upper right y1, and the second one is lower left x2, lower left y2, upper right x2, upper right y2. So this is lower left x2, lower left y2, and this is upper right x2, upper right y2, what's this point here? Well, its x-coordinate happens to be lower left x1. But in general, that's because this other figure happens to be to the right of it. But it might be this one that was the leftmost one, and that one to the right. So in fact what you want is the minimum of these two values. Lower left x1 or lower left x2. Whichever is smaller is the lower left x coordinate of the bounding box. So that's why the lower left x coordinate of the x coordinate of the lower left point is the minimum of these two values. And the y coordinate is the minimum of the two y coordinates here. So minimum of lower left y1 and lower left y2. So that explains this point here. That's the lower left corner of the bounding box. And similarly, this is the upper right corner of the bounding box. And I encourage you to sort of think about the picture and check to convince yourself that that's the right thing to do. Then another thing, I'm going to use those extents to decide when I put one thing above another thing. I need to know how big those things are because I need to know how far to shift them about so they don't overlap, they just touch. So those extents are going to be useful. And then I need to work out the extents of basic shapes. So I've got ellipses, I've got rectangles, and I've got triangles. And the extents of those, again, assuming them to be centered on the origin. So if I have an ellipse, and this is its x radius, and this is its y radius, then its extent, its bounding box, the lower left x coordinate is minus the x radius and minus the y radius, which is minus the two-dimensional thing, x radius colon plus y radius. So you get minus x radius this way and minus y radius takes you down here, and that's the lower left corner. And the upper right corner is x radius in the x coordinate and y radius in the y coordinate. So there's a rectangle around the ellipse there. My rectangle shape is slightly different. My rectangle shape I specify by giving a width and a height. And if I center it on the origin, then this point here is minus half the width to the left because the other half of the width goes to the right. And it's minus half the height down. So that's why there is the division by 2 for the rectangles. And for triangles, this is where you need the square roots of 3. And I'm not going to show you the geometry of that, but trust me, if you have an equilateral triangle whose side is S, then its center, the thing that's halfway between the left side and the right side and halfway between the bottom and the top, is the point with those coordinates, with division by 4 and square roots of 3 and so on. Seems unlikely, but that's what it is. So now, I want to find the extent of one of these, a whole one of these drawings. And a drawing is a collection of transformed styled shapes. Now, I'm going to ignore the style. The colour doesn't make any difference to the bounding box. The stroke width actually does make a difference to the bounding box. If you draw a shape with a thick stroke, that makes the bounding box bigger. I'm going to ignore that. So that's why I'm going to do this get extent to every triple, and I'm going to call the transform T, call the shape S, and ignore the style sheet. So that's actually slightly wrong. If you want something to do, you might think about what you need to do to take account of fat strokes when you're drawing a picture as well. But anyway, I have a list of these things, and so maybe there's a list with an ellipse and a rectangle, and I want to find the extent of the whole thing. Well, I'm going to do that by finding the extent of each individual shape. So there's an ellipse here, and there's a rectangle here, and there's a rectangle here. I'm going to apply get extent to each shape. So have you seen the function map before? Did you do that? Right. So if I know how to do something to a list element, if I know how to turn a list element of type A into a value of type B, then what map of that function does is turns a list of A's into a list of B's. It just does the translation from an A to a B for each list element. So here's my function, get extent, and it turns one of these triples into an extent, which is a pair of positions. And if I do that over the whole list, then it turns my list of triples into a list of extents. And so what's the extent of a single triple in the drawing? Well, if there's a shape, and I work out if it's ellipse, it's this big, if it's a rectangle, it's that big. That's the shape extent. That gives me a pair of coordinates. But then I need to deal with the transform. So if the rectangle is shifted, then its extent is shifted by the same amount. So if you shift it up to the right and upwards, then you shift its lower left corner to the right and upwards, and its upper right corner to the right and upwards by the same amount. So a transformation that is applied to the rectangle gets applied to its lower left corner and to its upper right corner. So that gives me a list of extents, but what I wanted was an extent. So drawing extent should take a drawing and give me not a list of extents, but a single extent. So how am I going to take a list of extents and make an extent? Well, basically you want to add all the extents together. You have a list of these things and you want to combine them into one. You want to add them all together, where the addition is this union operator that we talked about. So you just union together all these extents one by one. And there's a Haskell function called foldr1, which is like the foldr that I showed you yesterday, except you promised that you're never going to give it the empty list, and so it doesn't need a case for the empty list. And it doesn't need a starting value, so you just give it a binary operator. So this is also the thing that you'd use if you have a non-empty list of numbers and you want to add them together. You can do foldr1 with additions, and it'll add them all together. But here I'm doing foldr1 with union, and then we union together all these individual extents. Okay, and now here's how to, well, here's the structure of how to do my compiler. This is my compiler is turning a picture into a drawing. Remember, picture is one of these recursive tree-shaped things, and the drawing is one of these list of drawing instructions things. And my compiler is called draw picture, and it turns a tree-shaped thing into a list-shaped thing. And remember, there are three kinds of picture. There's just the basic place that just does a single shape, and then I can put one picture above another picture, or one picture beside another picture. And so to define my compiler, to define the function draw picture, I need to say what to do for each of those three cases. I'm going to write three separate functions: draw shape, which is what to do for the place case, above D, which is what to do for the above case, and beside D, which is what to do for the beside case. And they're all on the next slide. Yeah. So I have to define a function called draw shape that takes a style sheet of the shape and makes one of these drawings, and two binary functions above D and beside D that take two drawings and make a drawing. And it's not too difficult. It all fits on one slide. So this is basically a compiler on a single slide. Draw shape takes a style sheet and a shape and produces a drawing. And if your style sheet is U and your shape is S, then you need to produce a triple, which has got a style sheet and a shape. Well, those are both easy. And you need a transformation as well. So we don't know where the shape is going to be translated, so we're just giving the identity transformation. And then these two binary operators, it's a bit messy, but it's not difficult. So if I've got a drawing like this, and I want to put it, I want to put it, let's say, beside a drawing like this, which is centered on the origin. Remember, my drawings are centered on the origin. And I have another drawing like this, maybe it's just a triangle, and it's centered on the origin. And I want to put them together. Then what I want to do is make a drawing. I want to put them together one beside another. Then I want to make a drawing where this triangle is beside that thing. I'm going to align them on the centers. And then the new center should be the center of this whole thing. So this now needs to be aligned about here. This will be the new center of the picture. And so the net effect of that is that this picture needs to be shifted left, so that instead of the origin being here, it's here. And this picture needs to be shifted to the right. So instead of the origin being here, it's way over here. So now this picture is somewhere off the origin. So if you're doing beside, that's what happens here. You need to take your left-hand picture, which is a list of instructions, and your right-hand picture, QD, which is a list of instructions, and you concatenate them together to make a list of instructions. But you have to change all the translations. The left-hand picture has to be shifted to the left of it, and the right-hand picture has to be shifted to the right of it, and that's done by, well, this is working out the bit. Q lower left X is how much you have to shift by, and P upper right X is how much you have to shift by. And this transform drawing is another map. To transform a drawing left of it, you transform each of the instructions in the drawing left of it. So that's why there's another map there. And to transform a drawing, to transform a drawing right or left of it, you transform each of the instructions. To transform each instruction right of it, you've got a transform in there, and you have to transform it again. So you just compose those two transforms. And that's why the last line there, transform drawing composes two transforms, T and T prime. So that's complicated code, and talking about complicated code isn't the best way of presenting it. You need to kind of look at that and check that I got the right arithmetic with Q lower left X and P upper right X and so on. So I'll let you do that on your own time. And basically that's it. The practicals are then to kind of to work this out. Another thing you might do is to say, well, there's another deep embedding going on here. So let's go back. Pictures are this recursive data type, an algebraic data type. So there's a little language of pictures, and we've done a deeply embedded domain-specific language here. And this is a program in my deeply embedded domain-specific language, something of type picture. And then draw picture is the semantics. Draw picture takes a program in my deeply embedded DSL and gives you its semantics, which is a drawing. So we could do another shallow embedding there. We could get rid of the picture language altogether and just do everything in terms of drawings. You could have a shallow embedding. You could make your picture a shallow embedding instead. And then place, instead of place just being a constructor like it is on the slide, you'd make place do this. Place is the thing that gives you the drawing. And above and beside, instead of being binary operators on pictures, will be binary operators on drawings. And so you just kind of do a shortcut to get this code. That will be your language. Two other things you might want to do. You might want to try extending the language in small ways. And I've got two suggestions for you. So my stick figure was a bit naive because I could only put one thing above another thing, or beside another thing. I can't overlap one thing and another thing. So you'll notice there's a subtle difference between this stick figure and that stick figure where the arms meet the body. So the arms is this long, thin rectangle, and the body's a triangle, and the arms are balanced on top of the triangle. Because that's the only thing I can say in this simple language. But if I allow myself to extend the language so I can put one picture in front of another picture so they overlap, then I can allow myself to align things a bit better. So now the arms, the long thin rectangle, is on top of the triangle. It's obscuring part of the triangle. So I couldn't write that picture before, but now I can write that picture if I include another constructor as well as above and beside. There's an in front of constructor. And then on the right there's a chicken. Sort of. But to draw this chicken, I needed to have an upside down triangle. And how do I make an upside down triangle? I've only got right way up triangle, so I haven't got a way of doing upside down triangle. But let me extend my language again. Let me add another constructor, so as well as above, as well as beside, and as well as in front of, I'll have flip V, which is a vertical flip of a picture. So then I could make a vertically flipped triangle, and then I can put, so the eyes of the chicken is one ellipse on top of another ellipse. The two eyes, one beside another, an ellipse, and then a black rectangle and an ellipse. There's an upside down triangle, and then I have the eyes above a black rectangle above the upside down triangle, and that whole thing is on front of a big yellow circle, and that gives me a chicken. So you could do that. There's a little gotcha in that one, in that computing the extent of a flipped figure is a little bit tricky because the corners aren't in the places that you expect them to be. The lower left corner of a flipped figure is the upper left corner of the original figure, so you have to be a bit careful about the coordinates. And I think two other, so this is a bit that doesn't work. Josh, did you get anywhere? No, sorry. I'll see if I can figure something out. But in order to produce the diagrams that are in these slides and the ones in your notes, I've taken my compiled code, a list of triples with a transformer style sheet and a shape, and written something that converts them into SVG. I have to figure out how to do that because the code that we have to do in that no longer works. So let me see if I can make that happen. But anyway, once you know how to turn a rectangle into SVG and how to transform things in SVG, then you can make SVG out of all this. It can't be that difficult, so I'll set myself a challenge. I'm trying by lunchtime to get that SVG out and working. There's an interesting question here about, remember the thing at the bottom of the slide is to transform on positions, but we also now find ourselves wanting to do transforms on SVG diagrams in order to make the overall SVG diagram. So I need to invent a second interpretation of my transform language. So transform pulse interprets the transform as a pulse-to-pulse function. Transform diagram interprets the transform as an SVG diagram to SVG diagram function. That's two separate semantics. That works fine for a deep embedding because I just give two separate functions. For a shallow embedding, it's a bit clunkier. I could interpret my transform not as a pulse-to-pulse function, but as two functions, a pulse-to-pulse function and a diagram-to-diagram function, but better to make it a sort of polymorphic transformation. And the right way of doing that is with Haskell type classes, which I think you haven't really seen unless you happen to know about it before you came here to FLOLAC. But if I'm also right, then this afternoon's lecturer will be telling you about Haskell type classes. So having listened to this afternoon's lecturer, you could go back and reconsider this question. And I think I have one last point, which is just for fun. I'm going to add, so in my language I had ellipses, I had rectangles, I had triangles. Here's a fourth primitive. So I'm going to have a tile as well. And what's a tile? It's a square square tile with a particular side length, so that's the first parameter is the double, it's the side length of my square, and some markings on it, so some shapes on the tile, some drawings on the tile, lines on the tile. So here's an example collection of markings. A marking is a list of lines, and a line is a list of points, a list of at least 2 points. So this is the line from 4,4 to 60, and this is the sort of polygonal line that goes from 0,334 to 0,8 to 0,3, and there's lots more of those. That's a list of lines which makes a marking, and then so a tile is a square with some markings on it. And then I'm going to extend my transformation language with 2 more transformations. So as well as identity and translate and compose, I'm going to have expand that does some scaling in both dimensions at once. And I'm going to have a 90-degree rotation. So if I did that, then I wouldn't need to flip pictures. The point of doing that is that I can now do, these are 4 tiles, and tile, remember, is just a square with some markings on, so and the markings is just a collection of lines, so the top left-hand one there, fish P, is a tile with some kind of fish shapes on, perhaps you can see them, perhaps you can't. Fish Q, perhaps it's more obvious where the fish is there. These are sort of stylized versions of some tiles by Boris Escher, who did these famous sort of paradoxical diagrams. So I've given you the coordinates for those, so you don't need to work out what those shapes are. I've typed it all in. And if you manage to get tiles working, then you can put pictures with these tiles together. And why is that interesting? Well, it's because you can do this kind of thing. So these tiles are very carefully defined so that they fit together. So how is it going to work? Can't actually see where they fit. But, so this line here, this edge of this tile, precisely matches the top, so the bottom edge of the fish P tile precisely matches the top edge of the fish R tile. So if you put this tile above that tile, then the lines will match up. This line here will connect with that line there, and this line coming down will continue with this line along here. So anyway, you can put these tiles together and they make pictures, and where the markings reach the edge of the tile, the pictures line up, and so you've got a tile here and another tile underneath it. Actually, wasn't the alignment I expected, but you can see that this fish here from one of the tiles has its body in the top tile, and its tail, well, its tail is kind of here in the bottom tile, and they line up. But the clever thing is that if you rotate them and halve them in size and put them beside each other, they again line up. And Escher was very clever in designing the tiles to make that happen. So actually he designed the tiles to look like this. They're filled in and they have curves, and the curves are a bit more difficult for me to do, so this is an approximation. But this picture on the right here is something called Square Limit, and it's an etching by Boris Escher from 1964. This is from Wikipedia, but it's the image of the etching that he did. And this is my rendition of it. And as you can see, it's a kind of fractal picture. You've got these big fish in the middle, but then they get smaller and smaller fish as you get closer and closer to the edge. And they halve in size. And so they get tinier and tinier and tinier. It just goes on forever. It's an infinite picture in a finite space. Of course, I didn't make an infinite SVG file because it would never finish drawing, so